session, we're expecting to learn about the definition of assignment problem, its purpose, and how to compute for the optimal value or the assignments that produce the least cost using Hungarian method. The assignment problem is a special case of the transportation problem, which is a special case of the minimum cost flow problem. It is a special case of a transportation problem in which all supplies and all demands are equal to 1. Hence, assignment problems can be solved as linear programs. The problem instance has a number of workers and a number of jobs. And the workers can be assigned to perform any job, incurring some costs that may vary depending on the worker-job assignment. It is required to perform all jobs by assigning exactly one worker to each job and exactly one job to each worker, in such a way that the total cost of the assignment is minimized. Here, we represent worker as I, job as J, and cost as C sub I, J. Here is a network representation of an assignment problem with 3 workers and 3 jobs. Those on the left constitute the workers, while those on the right constitute the jobs. The network or lines example, worker 1 may be assigned to jobs 1, 2, and 3. Worker 2 may be assigned to jobs 1, 2, and 3, same as with worker 3. We can also represent the problem through a cost matrix wherein we let C sub ij be the cost of assigning the ith worker to the jth job. We define the cost matrix to be the n by n matrix. An assignment is a set of n entry positions in the cost matrix, no two of which lie in the same row or column. The sum of the n entries of an assignment is its cost. An assignment with the smallest possible cost is called an optimal assignment. Let us consider an example. I work as a sales manager for a cell phone manufacturer, and I currently have 3 salespeople on the road meeting buyers. Mark is in Cebu, John is in Calapan, and Tom is in Dipolog. I want them to go to 3 other cities like Cagayan de Oro, Baguio, and Boracay. Let us arrange this into a table. Rows represent the worker or the machines. Columns represent the job or task. And the values inside are the cost, time, or distance. But for this particular example, we're using workers, job, and cost. The problem is, where should I send each of my salespeople in order to minimize travel costs? We can represent the table as a cost matrix. Let's look at one possible assignment. Adding the 3, the total cost of this assignment is 11,000 pesos. Here's another example. If we sum these 3, we can come up with 10,000 pesos. Let us take note that the first combination of assignments resulted to 11,000 pesos. We can try until we get the least cost. For this example, there are 6 possible attempts, and the assignments that would produce the least shown in the screen. Where total cost is 9,500 pesos. 9,500 pesos is less than 11,000 pesos and 10,000 pesos. Trial and error works well enough for this problem, but suppose I had 10 salespeople traveling to 10 cities. How many trials would this take? There are n ways of assigning n workers to n jobs. That means as n gets larger, we have too many trials to consider. For large n's, or rows and columns, we can apply this theorem. If a number is added to or subtracted from all of the entries of any one row or column of a cost matrix, then an optimal assignment for the resulting cost matrix is also an optimal assignment for the original cost matrix. To find an optimal assignment, we can use the Hungarian method. This is an algorithm that applies the set theorem to a given n by n cost matrix to find an optimal assignment. Using the previous problem, the first step is we identify the least cost in each row. The minimum cost for the first row is 2,500 pesos. Second row is 3,500 pesos. And third row is 2,000 pesos. We now subtract the minimum value from the entries in each respective row. Say, for example, 2,500 minus 2,500, 4,000 minus 2,500, 3,500 minus 2,500, or 4,000 minus 3,500, 6,000 minus 3,500, 3,500 minus 3,500, and 2,000 minus 2,000, 4,000 minus 2,000, and 2,500 minus 2,000 pesos until we produce these values. In the second step, we apply the same procedure as we did, but this time we consider the columns. So the minimum value for the first column is 0, second is 1,500, and third is 0. We subtract these minimum values to their respective columns. So for example, 1,500 minus 1,500, 2,500 minus 1,500, 2,000 minus 1,500, and 1,000 minus 0, 0 minus 0, and so on, until we get this matrix. For all the zeros of the matrix with the minimum number of horizontal or vertical lines. Number of lines must be is 3, assignment of zeros is possible. Now, we give the assignments to zeros. In assigning, we should first consider rows with the least number of zeros. Row 2 has only one zero, so we give the assignment to this particular entry. Row 3 also has 1 0 and it's in 3. Or row 2. Row 1 has 2 zeros. Assign the first 0 because that particular row is already. Remember that we cannot assign one job to 2 workers, so for row 1, we consider the second 0. Replacing the cost matrix or the resulting cost matrix with the original, we can now get the cost for each assignment. This is now our optimal assignment. We simply add the values to get the summation of travel costs. If I ask my salespeople to travel on the same day, I will assign Mark from Cebu to go to Baguio, John from Calapan to go to Boracay, Tom from Dipolog to go to CDO. For this will only cost us 9,500. Let us solve another assignment problem. I'm required to move these bulldozers to four different sites are given in this. Question is, how should the bulldozers be moved to the construction sites in order to travel time? To solve, we follow the same procedure as with the first problem. First, we identify the minimum in each row and subtract them from the entries in their respective rows. For row 1, 5. So we mark it 7. 3.5. For row 3, it's 9. And for row 4, it's 4.5. So we just have to subtract the entries to the minimum. So 9 minus 7.5, 7.5 minus 7.5, or 3.5 minus 3.5, 8.5 minus 3.5, 11 minus 4.5, 9.5 minus 4.5, and so on, until we get this matrix. Next is we identify the minimum in each column and subtract them from the entries in their respective columns. So we just have to subtract each entry. 2.5 minus the minimum, 0.5, 2 minus 0, 6.5 minus 0, 3.5 minus 0, and so on, until we get these. Next, we identify or we cross out the rows or columns bearing zeros, making sure that we get the minimum number of horizontal or vertical lines. We have identified that the minimal number of lines our workers are 1, 2, 3, and 4, and our jobs are 1, 2, 3, and 4, and we only have 3 lines. So optimal assignment is not yet possible. If this is the case, we have to proceed to we have to note that 0.5 is the smallest entry not covered by any line. Subtract 0.5 from each uncovered entries. These are the numbers in blue or highlighted in blue. And we just have to add 5 to values covered by 2 lines. So 1.5, 1.5 plus 0.50 plus 0.5 until we come up with this matrix. We have to repeat step 3 by covering all zeros with minimum number of lines. From the resulting matrix, we still get 3 lines, which is less than 4. So 1, 2, 3, 4, not equivalent to our columns, number of columns and number of rows. So again, we have to repeat step 5. As we can see from this image or this table, our minimum value that is uncovered by any line is 1.5. So the first step or first procedure in step 5 is to subtract 1.5 from those uncovered entries. So we have to minus minus 1.5 minus 1.5 and so on. And we have to add start with rows with the least amount of 0, and that is row 4, having only 1. We have to cross out the other zeros in its column because we can no longer assign it to another bulldozer. Next is row 2, then row 1, and lastly row 3. Replacing this with the original matrix, we can now determine the amount of time needed to move a particular bulldozer to a particular site. We have assigned bulldozer 1 to move to site B, bulldozer 2 to move to site B, bulldozer 3 to move to site C, and bulldozer 4 to move to site A. All in all, the optimal value to move 4 different bulldozers from different garages to 4 different construction sites is 20. The number of workers is not equal to the number of jobs. Look at this table. We have 1, 2, 3, 4. While there are only 1, 2, and 3 projects, 4 isn't equal to 3. So let's if subcontractors a fixed fee plus mileage for the work performed. On a given day, the contractor is faced with 3 electrical jobs associated with various projects. So are the distances between the subcontractors and the projects. The problem is how should the subcontractors be assigned to minimize total cost? Since the Aryan method requires that there be the same number of rows as columns, add a dummy so that the first table shall appear like the one on the screen. We'll just have to add a dummy wherein the values inside it are zeros. Since all rows have zeros, we're simply just going to see the same cost matrix. Understand that the minimum entry for this row for Gencore is 0. So if we subtract 50 to 0, we'll just be the same. So step is disregarded or bypassed. So we have to immediately proceed to step 2, wherein we subtract the minimum value in each entries in its 50 minus 25, 28 minus 25, 36 minus 25, 20 minus 14. The resulting matrix is the minimum number of lines, all zeros. One can eyeball this minimum. Use the following algorithm. If remaining row has only 1 0, draw a line through the column. If our remaining column has only 1 0 in it, draw a line through the row. Having 2 lines, 1 and 2. Is it possible to have an optimal assignment? No, not yet. So we proceed to the next step. In this matrix, the minimum uncovered line is 2. We subtract 2 from uncovered numbers and 2 to all numbers covered by 2 lines. So we have to add 2 to 0. This is for the minimum number of lines to cover all zeros. Since the optimal assignment is still not possible because we only have 3 lines, we identify again the minimum uncovered number, that is 1. Subtract 1 from uncovered numbers, so we subtract 1 minus 1, 8 minus 1, 3 minus 1. We have to disregard these numbers covered by lines. To all numbers covered by 2 lines, so we have to add 1 to 0 and 2. From this resulting matrix, number of lines to cover all zeros is 4. Thus, there is a minimum assignment of zeros with this matrix. We now give the assignment to zeros. Again, consider the row with the least number of zeros. We start with row 1, then with row 3, with row 2, and lastly with row 4. Let us replace this with our original table. As we can see, the assignment for Arranger is our dummy project. So this means we cannot give Arranger any assignment. Finally, our optimal assignment is one shown in this slide. The total distance to be covered is 69 minus 19, having all 3. That's my presentation. Thank you for watching and listening. I hope you learn how to solve assignment problems using Hungarian method.